Welcome to the first doubt clearing session of Fundamentals of Additive Manufacturing. Today is the first session. This doubt clearing sessions will be basically like you guys are supposed to see or watch the videos and then come to the class. And whatever doubt you are having, I will try to solve them. You asked me in the class. And additional to that, sometimes it happens like people don't have much doubt. So in that case, I just try to revise what has been taught in the that particular week lectures, and like that we'll move forward. Along with that, uh,
Hello, చెప్పండి.
yeah, hello.
Hello.
Hello. Hello. Dhana Lakshmi Naidu. Yes.
No, ma'am. No, ma'am. మీకు కాదు.
Okay. Okay. Hassan Sabir, you want to say something? You are unmuted. No? Okay, so I would request you guys to be muted if you are not interested to say something, because this lecture is being recorded. Maybe I can make because this lectures will be recorded and posted in the specific YouTube channel. So if some of you are not attending the class on that day or not able to attend, then you can see or you can watch the videos later on YouTube. You'll be shared with the link. And so I was talking about the assignment. So there is a weekly assignment that you have to attend after every week's lecture. So you are supposed to watch the lectures and then supposed to attend the weekly assignment. There are points on it. So there are some previous year questions also available with me along with answers, but the questions are almost same. So I'll not discuss the previous year question in the specific week. So rather, I would like to have questions from your side. So it's better if you come up with some questions that we can solve in the class, and I can also come up with questions that we can solve in the class, and I will solve every week's question in the next week. Like if this is week 1, so the week 1 assignment will be solved in the week 2 doubt clearing session, so that for the final exam you will be more prepared. And in between, if you have any doubt, you can anytime mail me. There will be my email ID given to you all. I will have PPT, but I will not have much content, as professor has already discussed the topics very nicely. So I'll try to just add those images and input and data and information in my PPT. So I'll share that PPT as well. So as today is the first doubt clearing session, so I'll just start with the very basic of additive manufacturing, because I don't know whether you guys have already watched the videos or not. But before that, I would like to know about you guys, because it's very important for me to know which background you are coming from. Then accordingly, I can talk, I can speak or teach. So let's have an introductory session today. So first I will introduce myself to you, and then you guys can start one by one introducing yourself. So I am Ananya Nath. I am a third year PhD student in IIT Delhi in the Department of Mechanical Engineering. I am a bearer of PMRF, Prime Minister's Research Fellowship, under which I am attending this NPTEL TA-ship. So I'm supposed to do certain hours of TA-ship per year, and this NPTEL is one of the part of that TA-ship of for this semester. So currently, I'm in University of Turku, Finland. As a visiting researcher, I'm working here. I'm doing some of the research work here for my PhD, and I think and this is the last day at my college in Finland. So I'll go back to India soon, like next week. So next class onwards, I'll be taking lectures from my own college, IIT Delhi only. So that's about me. Now you guys can start introducing yourself, your background, or which degree you are pursuing right now. Should I call your name or you guys can just start speaking? Anybody can start?
Very good evening, Ananya. This is Dr. Mohammed Rafiq from Nair Institute of Technology. I'm an assistant professor in the Department of Aeronautical Engineering. My PhD is in parameter optimization and piece to departure modeling process for nylon aramid composites. This is all about me. Nice to hear about you.
Yeah, nice to meet you. Next, please keep on doing this.
Good morning, ma'am. My name is Nabil Mohammed. I'm currently pursuing BTech Mechanical Engineering. I'm third year student. Uh, Nice to meet you.
Then we have fast. Next. Yes, Faizan. I think we are not audible. You are not audible, Faizan.
Hello,
Hello.
good evening.
Good evening. Yes. We can't hear you. Till he fix his net connection. Somebody else.
Good evening, ma'am. I'm Vivek Sharma, third year mechanical engineering student from CSGM University, Kanpur.
Yes. Which department you are from?
Mechanical engineering, ma'am.
Okay.
Good
Next.
evening, ma'am.
Good evening.
Can you hear me?
Yeah, we can hear you.
Okay, my name is Shalom. I'm from Zimbabwe, but I'm currently doing my second year UG Mechatronics Engineering in
Okay.
Coimbatore, Tamil Nadu.
Okay. Nice to meet. Then
Nice to meet you too.
Good evening, ma'am.
it's good evening.
Good evening, ma'am.
Good evening.
I'm currently, my name is Dhanlakshmi. I'm currently pursuing 3x4 Mechanical in SLKR Engineering College in Bhimavaram. Nice to meet you, ma'am.
Same. Then
Good evening,
should I?
ma'am.
Yeah, please.
And good evening, everybody. I am Apurva Magdum. I am currently studying in Cummins College, Pune, Maharashtra. And I am in my second year mechanical engineering.
Okay.
Good evening, ma'am. Due to network problem, I was not able to introduce you.
Yeah.
Myself, Mohammad Faizan Khan, pursuing BTech in Mechanical Engineering from Aligarh Muslim University.
Okay.
Thank you.
Most of you guys are from mechanical. Okay. Good. Then we have next we have fast. Otherwise, I'll call your name. So Adnan, Apurva is done. Archini, Belal, then Gulam, Hamid, Hamad, Harsh. Anybody? Kiran. Pratik, Shan, Ramu, Prabal, anybody who can hear me? Come on, I haven't even started teaching you. Still you're not talking.
Good evening, ma'am.
Good evening.
I'm Hamid Raza, currently pursuing third year in mechanical engineering. Good evening, ma'am.
Good evening, ma'am.
Yes.
My
Adnan
name is
and
Mohammed Shakir.
yeah, yeah.
I am currently pursuing BTech third year from Aligarh Muslim University.
Okay. In which department?
Mechanical.
Okay. Then Adnan and somebody else was talking, I think.
Good evening, ma'am.
Yes. Good
My
evening.
name is Adnan Miraj. I am currently
Yeah.
pursuing BTech in mechanical engineering from Aligarh Muslim University.
Okay.
Hindi,
I think
Hindi.
a few guys are from Aligarh Muslim University this time, I think. You guys just have to keep on coming in the class. The days pass, people don't come, and if people come, they don't watch the videos. So I would recommend you guys to first watch the videos and then come. Even if you miss the videos, then also you come. I will anyway discuss about the gist of the topics that has been covered in that subsequent week. Anybody else wants to introduce themselves?
Good morning, ma'am.
Good
I'm
evening.
Hammad Hayat.
Yeah.
Sorry. Good evening, ma'am. I'm Hammad Hayat. I'm currently doing my third year mechanical engineering from Aligarh Muslim University.
And if you're joining the class, please try to be on time. Otherwise, if I start presenting the PPT, I will not be able to admit you all manually. So it's better to join the class within 6:10, not more than that. Okay, I think rest of you are not interested to introduce yourself. So I can present the PPT that I'm having. It's not much included there, but okay, let's start. Do you guys know anything about additive manufacturing? Or just raise your hand if you have watched the videos of week one. Who have watched the videos of week one? Please raise your hand. One, two, three. Three people? Only three people?
Myself.
Four. Four. I think five. You can raise your hand if anybody have watched. There is a button on top of the screen. 6, 7. Seven only out of 26, 27. Okay. So, can anybody tell me what is additive manufacturing? Just a one-liner question. What is
Raw
additive
material,
manufacturing?
raw
Yes.
material is converted into required mm,
Digital model
Yes.
to final
required
product
object.
through layer by layer.
Required object. By layer by layer.
Yes.
It's a layer by layer process, also known as 3D printing.
Yes. 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 Nice. Yes. So additive manufacturing, as its name suggests, it's a layer by layer material deposition process. I think I haven't mentioned one thing about myself. So I am doing my PhD in additive manufacturing itself. I'm working in laser based metal additive manufacturing. So I've already worked in few additive manufacturing processes. In my bachelor's, I worked in directed energy deposition, laser-based powder directed energy deposition. And after BTech, I joined PhD directly. It's my direct PhD. So in PhD also, I am working in laser-based powder directed energy deposition. I have also worked in powder bed fusion using laser beam. Previously, it used to be called as laser powder bed fusion, but recently its name got changed to powder bed fusion using laser beam, PBF-LE. So that's about me. I have also worked a little bit on SLA and FDM. So additive manufacturing is the layer by layer material deposition to get any complex 3D geometry from a CAD model itself. So in first step, we have the creation of CAD model. In the second step, we have to print the CAD model in 3D printing or additive manufacturing. In third step, we have to post-process it so that we can directly use the part which has got printed through 3D printing. So these three processes has their own specific terms and conditions, rules and regulations, process and process physics. So you should always remember few points about additive manufacturing. First, I don't have a PPT on that, but as you guys are from BTech mostly, so it's better to introduce the topic like that. That when I'm talking about the pre-processing of additive manufacturing, that includes the making of CAD model. Now, if you have already gone through the lecture, or just a second, I'll share my screen. I have to share the screen. Screen. My screen is displayed to you guys.
Yes, ma'am.
Is
Yes.
it visible? Yes, yes.
Yes, ma'am.
Okay.
Yes, ma'am.
So, yeah. So, as I say 3D printing, we have different varieties of 3D printing. I have pointed all the 3D printing techniques here. So there is wet photopolymerization, material jetting, binder jetting, material extrusion, sheet lamination, powder bed fusion, and directed energy deposition. And this is uh, the way the processes are mentioned is basically based on the energy that is being consumed by the process. So that means wet photopolymerization takes least energy and directed energy deposition takes the highest energy. So now comes the pre-processing part. So pre-processing means making the CAD model. So making the CAD model doesn't mean that you can just use a CAD software, for example, CATIA, SolidWorks, Fusion 360, and just make the CAD model and just print it. It's never like that. It's basically like if you want to use wet photopolymerization, you have to think from its own perspective. If you want to use powder bed fusion for making the geometry, you have to think from that perspective. So basically the CAD modeling or how do we make the model, that also depends on these processes. Because when we 3D print it, we 3D print it on a base. Basically how the birds make their own house. They find the strew, the raw material as the bricks, the dried leaves and everything, and they just put together everything in a small part of the tree branch, and then they make the house. Sometimes they make the house on a very stable ground or on a very stable branch of the tree, and then after making the whole house, they take the house and put it in a branch of tree which is suitable for them to live. So they are making it at one spot and then they are taking it to another spot where it has been used. 3D printing works exactly like that. When you 3D print the model, you 3D print it over a base plate. So if I have a book, if I have a sheet, if I have a metal plate or something, that is my base plate. And on the base plate, I 3D print my geometry. The 3D printing can be by powder form, like the raw material can be in powder form, wire form, liquid form, sheet form, bulk form, anything. So from there, you just putting some energy, that is the input energy, and then you are making the geometry. So the contact of your part and base plate is very important. If you can't understand this thing, I'll tell you again. So there will be a base plate, basically, or preferably a metal plate, onto which you will 3D print it. Because if you are from mechanical engineering, you might know about casting process. Casting is a process where we make the geometry from 0 to 100. In machining processes, we start making the geometry from a big block, which is 100, and then we cut it into specific dimension geometry, like subtracting parts, material, removing material, and then we make the final geometry. So we are starting from 100 and then we are making a geometry. But casting is a process where we start from zero. We don't have anything. We have the mold. We put the liquid metal into it and we finally make the 3D part. So it's like it needs the mold to carry the metal, liquid metal, and to give the liquid metal a shape while solidifying. Like that, 3D printing, in 3D printing, we are doing it layer by layer. So you have to put the first layer somehow, somewhere, so that the subsequent layers will be fused together to get the ultimate geometry. So that's why the base plate is very, very important in additive manufacturing. So in base plate or on top of the base plate, we print the 3D model or 3D geometry or 3D printed. So, like in different processes, we use different build plates. And for different processes, the process physics is very different. That's why ASTM has made this state of the art classification of 7 additive manufacturing process. So according to ASTM, so ASTM is a standard which we follow in various fields in mechanical engineering, in other engineering as well. From ASTM, they classified additive manufacturing into 7 different state of the art. What is state of the art? So state of the art means when your process physics is basically different for different processes. So powder bed fusion and directed energy deposition, these two are process where you can print metal. The metal has to be in powder form. In DED, it can be in wire form as well, but preferably in powder form, both the process. Both the process can use laser as an energy source. Both the process can be very accurate. Both the process can be very useful for metal part printing. Then what is the difference between these two processes? The difference lies into their process physics. So that makes these two processes as two different entities or as two different state of the art. So this is how this 7 state of the art came from ASTM to classify additive manufacturing. Now, if you are interested to make a 3D model or if you are interested to print something 3D geometry, then you may have to make the CAD model. When you make the CAD model, you have the 3D solid model, then you save it in .stl format. Then you import it in a slicing software. Then you slice it, and then finally you save the G-code M code for that particular machine and you print it. Now I have used already a few words like slicing, stl.stl, then for importing it for 3D printing. So STL is basically a file format which is supposed to be used to save the CAD model for the slicing software. Now, what is slicing? I already mentioned, you guys have already mentioned, 3D printing is a layer by layer manufacturing process. So we have to tell the machine that these are the layers you need to print per layer. Layer means if the 3D printing, this is the head of the 3D printing and it's moving like this, for example, to print something. So that head will have some speed. That head will, the some material will come out of the head. So the material which is coming out, it will also have some speed, that is called feed rate. So the head is moving in a speed, and the material which is coming out of the head, that has a speed. Then how much distance it will have from the build plate, or how much distance it will have per layer, that is also a parameter. Then how much heated up the head should be to melt the metal or to do the processing, that is also a parameter. The head will move in vacuum, or the head will move in argon environment, or the head will move in nitrogen environment or open air, that is also a parameter. So these are few parameters, and most important parameter, or one of the most important parameters, is the layer thickness. So how much thick layer it should print in one go, because it's a layer by layer manufacturing. So they are supposed to be hundreds of layers. So how much the layer thickness should be per layer? That is also one of the most important parameters. So in slicing, we tell this information to the machine. First, in CAD modeling, we make the topology, we make the geometry, and we make the topology. Geometry, if you have already watched the videos, then you might know. Geometry includes how much radius, how much dimension, how much length, how much curvature, these things, like diameter of the curvature. But topology include where the curvature should fit into two lines, or where the arc, this arc can have same diameter. But how the arc should look like in your geometry, that includes the topology. So in CAD model, you have to tell which thing you want to print. So this is my mouse. If I want to print this mouse, then this is a very thin mouse. It has curvature in it. It has two material. One I can see is the silver one. I can see the black one. So if I am using the silver, if I'm printing it, then maybe this time I'm printing two material at the same time. That also you can do. Two, three, multiple material also you can print at the same time. So if I want to print these two material, so I need to tell where the machine should change printing from one material to another material. Because at the starting, there is no such black part. It will just print the silver part only. From this much height, that black part is starting. So from this much height, it should start printing the black part and silver part all together, because it will be sliced like this, very parallel, 0 degree sliced with each layer, between each layers. So that's why in one layer it will print half of the black, then आधा white, और फिर आधा black print करेगा. So it will go like this. So these are the things we need to tell to the software or to the machine to print. So if this is my mouse, this is the topology of the mouse. So this curvature will have some dimension, that is the geometry, and this mouse will look like this. That is the topology. Now I can give you the information about topology in CAD software. So I'll make the CAD model. Then I'll save it in STL file format. So in STL file format, what does it do is basically it saves the surface data. Surface data means basically the topology. The surface data will be saved into small triangles. So it will subdivide this whole surface into small triangles. Triangles in such a way that their vertices, their sides should not be cut in between. The vertices, sorry, will be shared between can be shared between multiple triangles. The vertex, one vertex can be only part of two triangles, adjacent triangles, like few rules. But the whole surface will be covered by few triangles only. How small the triangles are, depending upon that, how accurate you can print. So then you are giving it to the slicing software. So slicing software needs to slice it. So basically, you need to tell what will be the feed rate, like at what speed the material will come out of the nozzle, at what speed the nozzle should move, at what environment the printing will take place. then how much heated up the nozzle will be. And sometimes, or most of the time, it's better to print in a heated build plate. I said build plate is very important. Build plate is something you need, and printing on heated build plate is also important. So those have some reason. I can talk about it later. So how much heating you should provide to the build plate for a better adhesion, for a better printing, that is also one parameter. How much the layer thickness will be, that is also one parameter. Or do you want to give some pause time in between each layer or not, that is also one parameter. So these are the few things that we tell the software by the slicing software. And then finally, after telling all the information, the software generates a G code encode. Basically, 3D printing is nothing but the CNC machining only. Machining doesn't mean only subtracting the material or removal of the material. Machining means machines doing some work. So 3D printing are also a kind of CNC machine. So they also generate G code, M code, and based on the G code, M code, they work. So you'll generate some G code input, you'll give it to the machine, and like that, the machine will start printing your part. This is the very, very basic of additive manufacturing. And the very, very basic should also include this point that your build plate, choosing the build plate, choosing the correct build plate, choosing the temperature, choosing the parameters, choosing the slicing software, CAD software, STL file, slicing, like layer thickness and everything. Everything is important. So if you are talking about additive manufacturing, then you should have this knowledge in your mind. Next time, if somebody asks you that I have a toy or I have a model, I want to 3D print it for my research or something, then which process should I use? So this is a commonly asked question people get when they are working on additive manufacturing. Like I'm working in additive manufacturing, so from other departmental students or other branch students, I get this question very often. Ananya, I'm working in some other domain, but I want to print this model. It's needed for my research. Which 3D printing should I use? Or you have a 3D printer now, I want to use it. You should know which 3D printing you should use based on which application you are going to perform, or your part is going to perform which application. Depending upon that, you have to choose your process. You have to choose the 3D printer. I have all type of 3D printer, but all the type of 3D printers are differently costly. Like some of them are very cheap, some of them are very, very costly. So you should not go blindly to the machine which can give you the highest accuracy or perfection with the crores of money. If it's not needed, then you should not go for it. If it's really needed for your work, then you should go for it. Because this 7 different ASTM state of the art has different applications. Like as I said, material jetting, binder jetting, or material jetting and powder bed fusion, which is, material jetting and material extrusion. These two processes can give you plastic parts. Okay, material jetting and material extrusion. And if you compare the cost of the machine, you will feel that I'm just taking some constant, but material jetting machines will be much, much higher costly than material extrusion machines. And they can also give you very, very accurate part. I think material jetting is one of the process, is the top accuracy printing process. I think no other additive manufacturing can give you that top level surface finish that material jetting can give you. So material jetting is that process. But you cannot go for material jetting for everything. Like this process is not capable of printing that much of metal parts. It's not very known. Material jetting is not known for metal printing. It can print plastic only. So if you have a very intricate geometry and very critical application of the geometry, you should go for material jetting. But if you have a plastic model which needs good accuracy, but it's application wise, its job is not that critical. It's not like you have to have few nanometer accuracy or something. You should go for material extrusion. You can save half of the cost. So this is how it works. Then sheet lamination is one process, not very much useful for these days, but yeah, then VAT photopolymerization. Again, for example, I'll give you another example. So VAT photopolymerization can also print plastic parts, but it uses liquid resin. So if you are printing through VAT photopolymerization, again, it can give you highest surface finish like material jetting. Not as like material extrusion cannot give you as high surface finish as VAT photopolymerization can give. But if you are running a toy industry, you cannot go for VAT photopolymerization because it uses resin, which is carcinogenic to health to some extent. And if you are making the toys, then it's not good to have VAT photopolymerization as a process to make those toys because children will eat the toys, will put it in their mouth, and it's not good for their health. So these are the considerations you should have before choosing a process to print some part. If you are learning additive manufacturing, you should learn it like you can give some idea to other people about this process because let me tell you, this is the process which is going on these days with high demand. Everybody is working in additive manufacturing, like even if they are not coming from additive manufacturing, they are using additive manufacturing because this is the hot topic these days. If you're really interested to do research afterward, this is very good to know about additive manufacturing. At least you can say that I attended a course and I have some few idea about it. And if you're somebody who is working in it, then whatever process you are working in it, but you should know these basic things like how to choose a process to print a part. Depending upon your material, depending upon the cost you want to invest, depending upon the application where you're going to put your metal or plastic part, etc., etc. So let's go one by one about the process of additive manufacturing. Can you see my PPT? It's in presentation mode right now.
Yes.
So this is VAT photopolymerization. In this process, now also remember that every state of the art also includes some processes. Like the state of the art name is VAT photopolymerization. But under VAT photopolymerization also there are multiple processes. For example, DLP, direct light uh, polymerization, direct light processing. Then there is SLA, stereolithography. Then there are other topics, other processes also. Right now I don't remember, but under the state of the art of VAT photopolymerization, there are different processes as well, and each process use different processing, but they come under the same umbrella or state of the art of VAT photopolymerization. In this photo, there is a this thing, which is a bill plate. So on the bill plate, this part has got made. This is the resin. So how it works like basically, if you see this is an SLA process. So this is a blade kind of, which is spreading the resin layer on top of it. And from this, the laser is coming. The laser is basically, the laser can come, the UV light can come. It's basically curing the resin. See, it went down. The build plate went down. The layer was spread. Now the light is coming to photopolymerize the resin which is present over there. So basically what happens is when you put the UV light on the photocurable resin, their monomers start reacting. They start making big chain polymers, and this is how the resin gets solidified. And the resin is a thermoset polymer, so once it is solidified, it cannot be melted again. So using this process, people use the physics of stereolithography to print resin parts. Now, resin can be of different color. They will be cured at different wavelength of the UV. So this process can be done by laser or UV light. So for laser, it's different. For UV light, it's different. For laser also, laser will have different wavelengths because it's light. UV light will also have different wavelengths. So if I'm talking about photocurable resin, then the photocurable resin will have the curing at different wavelength. So if I have purchased a resin of 532 nanometer for photocurable resin, then that means it can be cured at 532 wavelength light only, which is nothing but a laser light, like green laser. So the green laser will have 532 nanometer wavelength. So like that resin can only be solidified or cured under that green laser only. So that is how it works. But in this process, the build plate is going down by each layer thickness, and the layer is being spread using a blade, and the laser is curing the resin printed over it. Now this process can be reversible. The build plate can be mounted like this, and it can be dipped inside resin, like there is a vat of resin. This is also the same process, but there can be a vat of resin. The build plate can start curing from bottom. So in that case, the light will be given from the bottom. So this will be the UV light put on the resin, and it will be solidified, this layer. Then the build plate will move up by one layer. The resin will come. So the photo, like the UV light, will cure the resin present. Then the build plate again will move by one layer height, and the resin will be solidified like this. So when you get the build plate, the process is basically inverted upside down, but the product will be printed not upside down in its original way only. So this is another process. So SLA, DLP, these are different processes coming under the umbrella of wet photopolymerization. This is used for plastic printing only. Previously, it was used to be used for thermosetting polymer like resins only. But these days, people are trying to use the thermoplastic polymers as. So thermoplastic polymers means when you're curing, when you're solidifying the polymer, you can remelt it and resolidify it again. So there comes different process physics, but people are trying to use the thermoplastic as well. And it can be used for prototyping. Prototyping means if you want to print a real metal part, before the real metal part, you can start printing the plastic part in this process, then just check it for the real application. If it's good, then you can do the metal printing. If you can check that the part you have printed is good to go with for your application, then you can start printing it in metal, because metal one will be very costly. So it's better to start with the plastic one to check whether it works or not, and then go for the metal part. So the prototyping is good with it. For the toys, and again, toy not for kids, but some showpiece and etc., you can print using it. And as you are using resin, there will be transparent resin as well. So you can print a nice transparent showpieces and parts or gears, everything for showcase or some real application as well. These parts are often gone through the post curing technique again. So after the making the part, there will be resin everywhere. So first you have to wash it. Then it will be very glossy. So if you want to matte finish it, you can just sandblast it, grid blast it, or buffing operation you can carry on to make it matte finish. And then if you want to cure it more so that its density will increase and its hardness will increase, basically more solidification, basically more photopolymerization, big chain you are making of monomers, then you often go for curing process again. So basically you put the part in a UV curing chamber. From all that side, the UV light will come to cure the part better for better density. Next process. If you have any doubt, you can in between raise your hand and ask. Do you have any doubt? No? Good. So this is another process which is coming under VAT photopolymerization. This is polyjet printing. Polyjet printing means this head is having some nozzles in it, and the nozzles are connected to the supplier. From the supplier, the liquid resin is coming. So basically these nozzles are spreading the liquid onto the part, and from top of the head, this head is having the UV light or the laser light, which is curing this top layer, the liquid resin. Okay. So this is also one process. In this process, this part is not dipped inside resin. So the washing process after the printing will be a little bit easier. Next comes our, um, this is material jetting process. Okay. So here I have shown, is somebody trying to talk? It's fine. It's fine. Okay. This is material jetting process. So material jetting process also uses liquid material as a raw material. It will be polymers again. So these are mostly thermoplastic polymers. So thermosetting polymers as well. So both polymers you can use. And then this built material can be multiple color. So in VAT photopolymerization, if you're working with polyjet technique, then you can print multiple material, because here you have multiple nozzle in it, in this head. But if you're working with the serial lithography, it's difficult to print multiple material. So there comes this material jetting. It has a great finish in the parts, and it basically will have a nozzle, and from the nozzle, drop by drop, the part material will come. It will drop, it will come out from the nozzle, and it will get dropped on the build plate, and drop by drop, you fuse the the liquid plastic particles, droplets, they get fused together and they make the track, and they make the layer, they make the 3D geometry by layering. So this is very simple process. You feed the material in liquid form only. And then for each layer, for the solidification, you can use the UV lamp. Here something is called leveling blade. So basically it's like if you are spreading one layer of liquid, you can later use, after spreading the liquid on top of it, you can level it with the blade so that your part will not be inclined in any part because of the liquid surface tension and viscosity. So this is the process. UV lamp will be used to cure it, but it's not always. Like there can be metal jetting process that where the liquid gets solidified by itself. You don't put any UV lamp, but you can put as well. It depends upon the process again, because under material jetting there will be multiple processes. So, and also it depends upon the raw material that you are using. Next thing is, for VAT photopolymerization, for material jetting, we are using polymers, but your build plate will be metallic. Because for metallic build plate, it's better to bear the load of the part which is getting printed. It will be rigid because there will be vibration. There can be vibration because of the leveling up, moving up or moving down of the build plate. And this motion is controlled by CNC, lead screw, this thing's motorized basically. So there can be vibration, but this vibration is not good for your part. So it's better to have very smooth motor movement. And also it's better to have metallic build plate to bear the load and to be rigid. And it's easy to take out parts from metal build plate as well, because the metal and the plastic will have like a adhesion, not a bonding. So these are the things. So if you are using a polymer build plate, for example, there can be bonding of the layer at the polymer build plate. In that case, you have to cut the part after printing. So then it's better to use the metal build plate. So you can reuse the build plate again and again. It's not like one time use. So this is the process. Then we have binder jetting. So in material jetting, we are putting the material. The material is coming out of the nozzle. In binder jetting, we use the roller. Okay, so powder as a raw material and powder roller to put the powder on the bill plate. So basically the powder, if this is my bill plate, this is my powder roller. It can be roller, it can be blade as well. It will be used to spread the powder on the bill plate. And from top of the nozzle, like from the bottom of the nozzle, the head will be on top of the bill plate. And from the nozzle, the binder particles will come. Binder can be liquid, so this liquid binder will come and put the droplet on the area where you are interested to print your part. And when the liquid droplet is put on it, the powder particles will fuse together and then you can put additional heat to it. You can again put the roller on it to just press the part again so that it can be better adhered, or the adhesion will be better and the part density will be better. So this is the process of binder jetting. Material jetting, then binder jetting. Then comes the material extrusion. So in material extrusion, one process is called FDM. You carefully look at this process. So basically, there are two nozzles. From one nozzle, this is the next part, and this is the one part. This is two part. Two parts are there. Two nozzles are there. Two nozzles are putting different material in the part to make this two-part body. So material extrusion uses the wire form of the raw material. So here you use the raw wire form. Material extrusion is capable of printing metal and polymer both. How it works? So the nozzle, so in any additive manufacturing process, typically there will be a nozzle. So I will use this term nozzle again and again. So you understand when I say nozzle, you understand I'm talking about this head from which the material is coming or the energy is coming, something related to the printing. So from the nozzle, the wire will come. But the wire is in solid form. How the wire will get melted and deposited? So basically in the nozzle, there will be heating coils. First, there will be pulley to put the tension in the wire. When you do like this, you're basically putting the wire in tension so that the tension will not let the wire bend in between. Then also, if you are decreasing the gap between these two pulleys or these two rollers, then you are also squeezing the material. Basically, आपने उसको ऐसा कर दिया एकदम, मतलब जो diameter of the wire, you are basically decreasing it, you are squeezing the material. So now you have squeezed the material that makes the wire in a semi-solid form. Not semi-solid literally, but you are putting some heat and you are softening the material. Then the wire is passed through the heating coils. If the heating coils are there, so it basically heats the wire. So now the semi-solid wire comes out of the nozzle. So the wire which is getting deposited here is not fully liquid. Yes. Yes. Hello. Somebody wanted to say anything? Okay. Here the material which you are depositing is not in a liquid form. It's in semi-solid form. And the semi-solid wires, you are just depositing one by another, one adjacent to another. By that, you are putting the layers on top of each layer. And by layer, you are making the object. So in previous slide and in this slide also, there is something called support material. Know what is it? So when you make the 3D printed geometry in casting, compared to casting, you make the mold in casting. And in the mold, you put the liquid metal. So wherever there is space, the liquid metal will try to flow inside and just try to fill it. So that's the process. But if I am printing it in 3D printing, then basically this is my build plate. So for example, this copy is my build plate, and from the nozzle, the material is coming and printing things like this. Cool. Now, if I want to print this geometry, this is the geometry. So it has a lower curve, then a line, then upper curve, then a small line. So this is the geometry. And there is material in this part and there is no material in this part. And if I want to print it like this, then do you feel that when I'll be printing it, there's supposed to be some material, otherwise this part will fall down, right? So if I'm printing this part on top of the build plate, obviously the part I'm printing here will fall down if I don't put anything over here. Just like how bridges work. If you're putting a bridge in a road or if you're putting a bridge on a river, then you just don't connect it. You put some columns in the bridge from the river as well, just to stand the bridge. Otherwise, the bridge will fall. So similarly, in additive manufacturing, as the nozzle moves like this, so if I'm printing this part, the nozzle will deposit material here, 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 then here, here. So like that. But if I don't put anything in between, then this material will fall. So that's why we put support material there. That is written here, support material. And this part is called overhang. Overhang, it's hanging part, so that's why it's called overhang portion. So that's why I say that pre-processing is also very, very important and it's very critical as well, because when you're making the CAD model, you have to take consideration of these things as well, that if your model is having too much overhang portions, you have to put support material everywhere. There will be some structures which are self-supported, or there will be some structures, for example, this bottle. If I want to print this bottle on top of this diary, then I don't need, and this bottle is fully solid. There is no void inside it. So it's just a column I'm printing. So there is no support structure needed. You can simply print it till here. But if this bottle is empty like this, then this portion will be printed, this portion will be printed. But when you put this dhakkan wala portion, no, you need some support structure, because at this surface, there is nothing below it. There is just vacuum space. So that's why from the top to bottom, you'll need a support structure. So this is how additive manufacturing works. Now, if you put the support structure, then you can say, I can put any block. I just put the block in the CAD model itself so that the part will not fall. But you have to remember a few things. You have to remove the support structure after printing. So if you are putting a real part into your CAD model as a support, the part will have same density as your actual part. And it might get difficult to remove the support from the part without destroying the part. This is one thing. Next thing is support structures are typically or basically the waste of money, because ultimately you will remove the support. When you remove the support, you will lose the money invested in the material. You will lose the time which you invested to print the support. You will lose the energy that was been invested to print the support. So these are the things, few things like material, cost, print time, everything which I have invested to print the support will be removed. Will All these are lost, nothing else. So that's why support design itself a study in additive manufacturing. But the basic concept of support is to give the physical support to the overhang parts. And in this video, if you remember, the part is actually looking like this. And this, what color it is, I don't know. But this small portion is actually support. Maybe there is a big circular hole and on top of it, I'll print the part again. That's why maybe somebody is putting support here. Or it can be multi-material deposition as well. But I think it's multi-material deposition, not support. Because if it were a support, then I could have just put this type of columns as a support, not fully dense material, because it will be very difficult to remove this dense material. So we don't fill the all overhanging portion. We just put some stands on top of it, on below the overhang portion, so that it will withstand that its load. We don't put the whole solid body on below it. We just put stand like this. So this is support structure because we have to remove it. It's the removed part, so it will include some cost. So this was the material extrusion process. Next comes the sheet lamination process. Sheet lamination is a process where it's a process which is used for prototyping only. It's not much used for real part production. And these days, I think nobody uses it. So sheet lamination is a process which was very well known previously before because it was very good for prototyping. So the sheet of paper you can use. So this is a roller, for example, where you have rolled all the paper. So there's a big length paper which is rolled into the roller. Okay. Now the paper is coming from here to here, and now it's getting rolled in another roll. Okay, so there is a big length paper, very long paper. One end is rolled here, this part, and the rest of the paper is rolled here. So the paper will come like this. There will be a cutter, typically a knife, very sharp edge knife. The knife will cut the paper in such a way that that cut portion will itself be a layer of your material or part to be printed. Then comes the energy source. So it can be, if you are printing some wooden part or something, wooden sheets can also be used. In that case, some laser light or some energy source you can put to join wooden parts. Otherwise, if you're printing papers, then they just put a heated roller onto it. This is the heated roller. It will roll onto the paper and the paper will be fused with the previous paper cut. So when it's fused, the roller will again roll. So the paper which is having this cut part will go and the new paper will come. The knife will again cut it like in this. They are making a ring. So the ring wise, the paper will be cut. Again, the roller will come, roll over it. Because of the weight of the roller and the heat of the roller, the two sheets which have been cut will be fused together. And this is how the paper will continuously come through the roller because it's a very long sheet and the roller will heated roller will just press these papers together to fuse them. And how you are defining the layer, you basically use a knife to cut, not you, the machine uses a knife to cut the geometry in the paper. So this is how it works. Now, for the cutting also, you can use laser if you are using any wooden job or something. For paper, knife is enough. Then comes your directed energy deposition. In directed energy deposition, so first should be powder bed fusion, then directed, but it's okay. Directed energy deposition is also known as DED. DED. So directed energy deposition uses metal. You can't use any polymer in DED process. DED process cannot print polymer. It is only used for metal. Then DD process can use the powder and wire, both form of material. It can deal with both form of material. So, and as we are using metal, so your normal laser or normal UV light or this heated roller or any kind of light source or whatever we have seen till now, heated coils or something, this will not be useful for metals because the metal, for example, aluminium, which is having at least the melting point of 660 degrees centigrade, obviously your heated roller or UV light will not help. You need a high power laser beam. Now, laser has its own physics, it has its own introduction and big chapters. I'm not going into that. If you have any doubt, you can ask me anytime. But the laser is basically a light source which is having very, very high energy, which can cut a human being from into two halves, basically. That high power laser we use. The laser is coming. So this is a nozzle in this case. This black part is a nozzle where there is a central slot in it. So through the central slot, this white portion, the laser is coming. And there is some circumferential slot. So if you see the cross section of the nozzle, it will be circular. In the circular, there will be a central slot and some circumferential slots in it. So from the circumferential slots, the powder is coming. Powder means metal powders. The powders are coming, the laser is coming. They both will meet at one point. All two materials, like the material and the laser will meet at one point. And at that one point, the material will get melted because it's very high power. And then it will, the laser along with the material, basically the nozzle will start moving. So if this is my build plate, this is my nozzle, it will start moving. So it will move like this and deposit the material. As soon as it moves, the material gets solidified, which was melted because of the laser. So this is how directed energy deposition works. If it's not clear, I can tell it again. The substrate should be metallic as well. And this is how it works. So you see from the nozzle, this is the nozzle. The centrally the laser is coming. Circumferentially the powder is coming and they are both meeting at a point and the thing is getting melted and deposited. Okay. So this is how they are making a turbine blade kind of thing and metal part. And if you have a nozzle which is mounted on a robotic arm instead of CNC, and your build plate is also mounted on a robotic arm, then it can have more than 3 degrees of freedom. If it can move like this, then if you have a part like this, you can simply print like this. You don't have to print like this so that you have to put the support. You can just print like this and you don't have to have any support. So if you are having more than 3 degrees of freedom, you can start avoiding support. Mark the words, you can start avoiding support. You cannot avoid all the supports, but at least if you are having 5 degrees of freedom, you can have supportless printing because it's rotating also, it's moving also, so you can have supportless printing. This is this is how people previously used to print in three axis degrees of freedom CNC. So they have to have support, but using this robotic arm, you can have without support printing as well. But some processes like wet photopolymerization, they are dealing with this liquid resin. They can't have more than 3 degrees of freedom. So that's why supportless printing in those cases is quite difficult. Then comes material jetting. It's also a liquid part coming onto it. So not possible. Binder jetting. Binder jetting, you're spreading the powder. The powder thickness, the layer thickness will be in micrometer. Maybe 30, 40, 60, 100 micrometer. Our human hair thickness is 100 micrometer, less than that layer thickness you can get. So that's why it's not possible to have more than 3 degrees of freedom in all the cases. but where it is it's possible, people use it. There comes another process. So as a raw material, I said we can use powder and wire as well. So this is the wire-based deposition. You see from the nozzle end, this wire is coming, and then somehow it's making some energy which is shown in this bright light, and it's printing the part like this. This is layer by layer because you can clearly see the layers. How it works? So basically in DD, I said the raw material can be in powder or wire form, but the energy source also can be arc, plasma, instead of laser. So laser, arc, plasma, these are the options you can have in DD. Now, plasma is also an energy source. You can read about it. Arc, we all know. So basically, if you are from mechanical, you know about arc welding. You know about MIG, TIG. So tungsten inert gas welding will not have a consumable electrode, but this metal inert gas arc welding will have a consumable electrode. Now, think about it. Instead of just doing a T joint, if you start depositing that metal consumable electrode onto the build plate layer by layer, you can get a 3D part. So this is how the additive manufacturing actually came from the spray or coating techniques and the welding technique. So this is how it works. Okay, so DD can include powder and wire, both form of raw material, and it can uses multiple source of energy. Next comes the powder bed fusion. According to me, this is the most tricky process along with DD as well because it has a very fine powder distribution. DD uses the powder distribution from 45 to 105 micrometer like the metal powder you are using. But in LPBF or PBF, powder bed fusion, we use 15 to 53 micrometer power, much lesser. There will be this roller or a blade kind of, which will spread this powder in 30-40 micrometer layer thickness. Layer on the bill plate. This is the bill plate, which is connected to a lead screw or something, CNC. This bill plates comes down, moves down by each layer thickness. The roller spread the powder like binder jetting, and instead of binders, you are putting energy into it. So that's how these two state of the arts are different. In bindless jetting, you're just putting binders. You can do polymers. But in LPBF, your process physics is itself different. You're melting the metal powders. You're melting the powders means you're changing the property, metallurgical property of the material. So the laser will basically scan or the laser will move like this very fast on the bill plate where the powder is spread only at the position where the part needs to be printed. The other part will be in powder form only. And like that, each layer will be spread and the laser will only move in the portion where the part needs to be printed. So after the part is been printed, you can simply remove all the powder from around and you can get the part. But here in DD and PBF, you're printing the metal parts on the metal bill plate. So that's why you have to cut the part from the bill plate using any mechanical tool or any band saw or wire EDM, some process. So there will be metallic bonding between the bill plate and the part. And it's also needed for the metallic part to be printed. For plastic processes, you don't have any bonding between the metal plate and your part. There is just adhesion. You can just put water or you can just heat it and the part will come out from the build plate. Or you can just bend the build plate and the part will come out. But for metal printing, you need much thicker build plate like 10, 20, 35 millimeter build plates to sustain the heat because there will be a lot of heat to melt the powder, metal powder. There is another thing in PBF, as you can see from the process, PBF can print only powder material. The material has to be in powder form. Next, PBF can work with laser or plasma, but not with arc. Uh, Electron beam can also be used in PBF as an energy source instead of laser. Third, powder bed fusion is typically used in a controlled atmosphere. The other processes were not in that controlled atmosphere, but in PBF, there will be 0% oxygen inside the chamber. There can be vacuum as well because of in case of the electron beam, it will be fully vacuum. In case of a laser, it will be either filled with argon or nitrogen. So no oxygen present so that your part will not get oxidized at the time of printing. These are few considerations. Another one is powder bed fusion can never use the wire as a raw material. There is another surprising fact, which is powder bed fusion can be worked with polymers as well. So under the umbrella or under the state of the art of powder bed fusion, we have few more processes. One is called SLM, one is called SLS. SLM means selective laser melting. SLS means selective laser sintering. Selective metal laser melting means the laser is selectively melting the powder particles to get them fused together and make the layer and then subsequently make the part. Selective laser sintering is the laser is selectively sintering the powder together. The powder is getting fused together, but they are not getting melted. So their metallurgical process is intact even after the printing. So this is the basic difference between the SLM and SLS. So these are the two PBF processes we have under the umbrella of powder bed fusion. So these are the 7 different state-of-the-art of additive manufacturing according to ASTM standard. I haven't mentioned many other processes which are coming under the 7 state-of-the-art umbrella. Sorry, which you can later find out in Google. You can search on it. You can have a look from YouTube as well. But these are the 7 process physics which is important to know. And also now you know which process can print metal, which process can print the polymer. And this
Excuse
is
me, ma'am.
how, yes.
I had a doubt, like what is the difference between that unfused powder and fused powder?
So it's not unfused. So are you talking about the powder which is here? This is unfused, this is fused, or SLM and SLS?
No, the one which is written there on the screen.
Photo. Okay. So
Yeah.
if you see this part, so this blue is the powder. Okay. This has been spread. And this A at the rate, this is the part that is been printed. So basically this powder is the unused powder. So unfused powder. Like I said, now after printing the part, you can just simply brush away all the powders which are present in the surrounding and you can get the part. So this is the part which is being printed. So in the part only, the laser will melt the powders and make them fused. But around the geometry, the laser will not melt the powders. So this will be unfused powder. This will be loose powder. You can just brush them away and you can get the part. And fused powder means here if you have a part, right? In the part, you can't distinguish the powders. You can have the intact metal tensed part in which the powders are already melted and solidified to make the proper metal part. But in between the part, if you see the geometry, it's an at the rate. So there is lot of powder which will be present inside the at the rate geometry. And these powders, like few of the powders which is near to the boundary of this part, may get fused together because of the heat. The laser didn't move on this part where the powder don't need to be melted. But because of the heat of the part, these powders got fused. So you can just sandblast them or you can use any post-processing process to remove these powders. Fused powder means these are not melted. These got fused because of the heat. And unfused means these are the loose powder. You can just brush it away. because this loose powder is present because of this layering. If you see this video, this is how LPBF works. You see, this roller is spreading one layer of powder. This blue is the powder. Excess powder is collected in the bead. Now the laser is coming, scanning, it's melted and fused. And like this, the roller is again spreading the powder. The laser will again come and melt the metal and make the part. Now you think about this geometry. This geometry don't have any support. Okay, it's supposed to have a support, but I don't know why in this video it has shown there is no support. Let's take this example. Now in this geometry, in this area, very close, very close to this wall, there can be some fused powder particles which are sitting on the surface of the part because of the heat that you can consider as a fused powder. And in this part, the powders are already melted and solidified. So you can't distinguish the powder. And in the blue part, in other area, these all are unfused loose powders, which you can brush away after the process and you can get the part. Is it clear?
Yes, ma'am. Got it. Thank you.
Yeah. So this is how LPBF works. That's why I said for understanding LPBF, it's a little bit tricky to understand. It's easy to understand other process as it's very unrealistic to think that that is possible. There is a possibility to layer to spread 30 micron thickness of layer of powder. It's very unrealistic to think. When I got to know about the process few years back, I was shocked that is it possible to spread 30 micron layer thickness of powder, because our human hair is 100 micron thick. 30 micron is so less. So that's why it's sorry, human hair is 100 nanometer. But still, it's very shocking to have 30 micron layer thickness spread over the film plate. So it's a bit difficult to understand, but when you see the process, you understand better. So you can just search in YouTube and you can see the real processing videos there. So that's all about the 7 different types of additive manufacturing. If you have more doubt, you can ask now, or you can if you have doubt afterward, you can just note down the route and ask me the next class. In previous year, I have also taken other courses. So there people used to mail me their doubts before the class as well. So that also you can do. But I would prefer you to ask in the class so that other people can also know about your doubt and clear their doubt as well. So these are the 7 processes. So now why people are joining after 1.5 hours, I don't know. So now we can start seeing the previous year questions. And if you have any idea about additive manufacturing, or you have watched the videos of week 0 or the preliminary one and any other thing, you can just try answering the questions. So if you know the answer, just unmute yourself and tell me. LOM stands for laser object manufacturing, light object manufacturing, laminated object manufacturing, or locomotive object manufacturing. Anybody?
Ma'am, laminated object manufacturing.
Laminated object manufacturing. It's basically sheet lamination process. Which type of CAD file is mostly used in 3D printing machines?
STL.
STL.
So, yes. No, it's STL. So CAD file format. So basically the CAD file is has to be saved in STL to go for the next process, which is slicing. SLA stands for
Stereolithographic apparatus.
yes. Yes. Stereolithographic apparatus or just stereolithography. What is the use of doctor blade in 3D printing?
Remove extra layer from.
One answer. The second answer is So it's the layering, okay, doctor blade is removal extra material from the build plate, but doctor blade is also used for the layering of the part. So layering of the part means the blade you seen in my videos, in my uh, photos that I put, that is also called the doctor blade. So basically as a recoater, okay, in LPBF, the blade which is used to spread the powder is also called the recoater. The recoater can be a blade, can be a brush, can be a roller. But this recoater, instead of recoater, some people, some machines called it doctor blade as well. So these have both this can have both the use.
Ma, ama
Yes.
పెట్టేకు నేలనేసి కొడతాను ఒకటి బడిపా
Next. Okay. Next is STL.
Asian language.
All
Standard
three of them.
language.
Third option.
BNC.
Standard.
Option C.
All three of
BNC.
Okay, so it's B and C. It's not
BNC.
selective. It's standard tessellation language or standard triangle language or stereolithography. The first option is selective triangle language. This is wrong. It can be standard triangle language. So read your questions carefully. The tools and fixtures used in additive manufacturing process are dash the object geometry.
Independent.
So it's independent to the object geometry, but when you're talking, because when you're talking about the doctor blade or the recoater or the heating coil or the heating blade, these are independent to the object geometry, obviously. But if you are talking about some fixture in some additive manufacturing, very few, like you're making some fixture to fix the part in it, it can be dependent as well, but mostly it's independent to the object geometry. So the support is required to realize the dash features of the object. Identification of the region required support is carried out at the dash stage.
First overhanging and pre-processing. Sorry,
So when
overhanging
we
and
call it
post-processing.
overhanging,
Overhanging and post-processing.
okay, so it's overhanging, but identification of the region required support is carried out at pre-processing. At post-processing, you can remove the support, but identification of the support, like if you have make the CAD geometry, you have to identify where you need the support. Otherwise, at the time of printing, it will be failed. Your whole material is wasted. So you have to identify first where is the support required. Then you put the support there, and then you finally save the file for the printing. In the slicing step, we put the support, but the identification of the support, we do it in the pre-processing step, which is the CAD modeling preparation. Also, I forgot to mention, it's not that you always need the support. If you want to put this part, if you want to print this part like this, you need a big void which needs support. But if you just print the part like this, you don't need the support, right? Because this will not have that much part. So you can minimize the use of support depending upon your application, depending upon your requirement, and you can orient the part like this so that you need the least amount of support. Also, another point I should mention here, when you're putting the support, maybe you thought, if I put the part like this or this, the number of support will be same. The time for the support, the cost, money of the for the support, everything will be same. So there is no difference. There is still some difference. It depends on the part that you are going to put in some application. So if your application permits some surface roughness, whether your application permits of surface roughness in this part or this part, Depending upon that, you'll put the support. Because wherever you put the support, there will be some surface roughness because you'll remove the support. There will be some residue of the support on your part as well. Then you have to remove it again. And if you don't want to remove it, then there will be surface roughness. So if you can um, sacrifice that much surface quality on this part or this part, depending upon that, you can fix, you can identify, or you can decide whether to put the part like this or this. So that is called part orientation. Orienting the part is also important. It's not like you want to print this bottle in this direction, this direction, this direction, or this direction. You can print it in different way. It's your decision how you want to print. Because in this direction, it will take less time. In this direction, it will take more time. In this direction, again, it's intermediate time. In this direction, there is no support. This direction, there is lot of support, but less time. This direction, medium support, medium time. Then which one do you need? Can you invest more time and get a part which is smooth because of no support? Then you prefer this direction. If you can sacrifice the surface because of the support, and then your time is optimized, you need less time to print, then you print in this. If you need both, you need intermediate surface roughness and intermediate part, then you put in this direction. So this is the way you should optimize your process. You should optimize the part printing. It's not very simple thing. Even the CAD print, even the build or formation of CAD geometry is not simple. Building or orienting the part on the build plate is not simple. Selecting the part parameter is not simple. Selecting the support structure is not simple. So that's why you need to go deep inside this topic and think about it before doing it or before advising somebody to print their part in some process. The last question is, a digital image is composed of pixels. Similarly, an STL file is composed
Triangle.
of
Triangle.
yes,
Triangular.
triangles.
Triangle.
Can anybody tell me why triangles?
Because it's collinear and simple compared to
Because it's collinear.
Non-collinear.
non-collinear. Non-collinear.
What
It
is
is
non-collinear?
coplanar and collinear.
Triangle. Non triangle.
Coplanar and
This
collinear.
and same line does not same lie on same line. But this or does not lie on same line. That's called non-collinear.
Because they
Non-collinear what?
the
Non-collinear when it doesn't it's not in same line. It's called non-collinear what? Triangles. So when your 3 points are not in same line, that is the non-collinear points, and these 3 non-collinear points can make only one surface, which is called a triangle. So basically, why triangle? Because triangle is the surface or is a geometry which can cover the full surface using only 3 vertices and 3 sides. Basically, least amount of lines are needed to make a surface. So triangle is one geometry where you need the least amount of lines to make a surface, which is the 3. 2 points can make a line, but 3 points which are non-collinear can make a surface, which is triangle. And STL is something in which you are basically covering a full surface using a geometry. And triangle is that smallest geometry which you can put in the surface to cover it. So that's why triangle. And to make a triangle, you have to have the non-collinear 3 points. So it's triangle. And that's about it. This is my email ID. One is my institutional email ID, this MEZ one, and this is my personal email ID. You can mail me your doubt. You can mail whatever doubt you have, whatever queries you have, anything else, any suggestion, you can For official communication, I use mail. I'm always active on it. So if you want to discuss anything, you can just mail me.
Is this
Otherwise,
video will be posted in posted?
yes, yes.
Because
There is
first
a
half an hour I was absent. That's why.
yeah, it's okay. I will post it. So how to stop share? So I will post this video anyway in YouTube, and the channel link I will send to the NPTEL team so that they can just mail you all the link, and you will get a link where you can find this PPT as well. You can find the diagrams. In this PPT, it's not that much informative because it's just the videos and photos, images you can find in Google and YouTube as well. And as this was an introductory class, so that's why I wanted to cover very introductory topic about additive manufacturing, just to clear about the topic, about the process. I will not extend today's class much.
In NPTEL assignments, there are some checkbox. If the checkbox indicates there are multiple answer or single answer.
I have to check. So generally it's circle.
Yeah, circle
No,
means
it
one
is just
option.
Yeah, then check marks means it can be multiple options.
Okay.
Yeah. So
when we will
assignments
have
are
when we
sorry.
will have our next session, because when we look at the second assignment, it consists most of them are problems. So if there is a session for us, it will be good. First assignment we can solve very easily, but second assignment, and we didn't go through the slides also. We will go through meanwhile, and if there is a session, it will be good for everyone. I think. What others feel?
Yeah, problem is little bit new to us in additive manufacturing. So if you solve some problems or if you suggest some textbooks to read, also it will be better for us.
Okay. So truly speaking, I never read a textbook in additive manufacturing because it's so new field. So I have never read any textbook on it.
So
I just
for
read
problem solving,
research.
only I'm
Yeah,
telling.
problem solving also I have never tried it, but for the NPTEL, I can just try solve. I can solve the problems, but the only thing is the problems which I am having from previous. So basically, I'll tell you clearly about it. So we the TAs are supposed to solve the previous year questions in the class so that you can attend this year assignment. But unfortunately for this course, the previous year questions have some similarity in with the this year questions. So that's why I was a little bit confused whether I should solve it or not. It's not true for all the weeks, but it's true for few questions and few weeks. So then if you have a lot of problems, then I can just start solving the previous year problem from next class onwards. So in next class, I will solve week 1 and week 2, both the assignments together, so that
Fine.
week
Fine.
2 or week 3 onwards, it will be clear for you all.
Ma'am, if it is
It's
similar, if you fail, if it is similar, at least tell the concept how to solve.
Yeah. I can tell you the concept as well.
If it
So
is
And
if you
ma'am,
found similar,
one thing.
tell me the procedure to solve because no
yeah,
textbooks are there, reference are there. You tell
yeah,
me the
Exactly.
procedure. Okay.
Because the thing is, around 30 to 40 students are doing this course in my institution. I'm the mentor for them. So there will be a common discussion session for all of us to solve the assignments. Only if we know
okay,
the concepts better, it will be good for us to explain them so that it
yeah,
gives them more and more interest in this course because it is a 12-week
yeah,
length course. So it
yeah.
is not easy for
Sure.
everyone to do it. I hope you can understand.
Yeah, sure. I understand. So generally I solve the question in the next class, but it's okay. I can start solving it from next class onwards. Like in week 2, I was supposed to solve the week 1, but I can solve the week 2 as well. So then next week onwards, we will start solving the question. I will have a small recap on the topic that has been covered in week 2, and then we'll solve the questions, clear the idea about how to solve the questions. And if you have some question from your side, it will be very good to discuss that as well.
Sure.
Yeah. So I would request you to please go through the lecture, all of you, and try to attend the class or try to come in the class on time. Maybe 10 minutes is fine. Like from 6 to 6:10, you try to join so that I don't have to admit you all every time in between the speech. Cool. So then we can stop the session here if you don't have any question.
Yeah, thank you, madam. Thank you so much.
Yeah.
Yes, ma'am.
Thank
Thank
you.
you. Kindly, madam.
Thank you for attending.
Thank you, ma'am.
Have a good night.